To determine the subfeed cable size for central electric heater rated at 15 kilowatts and a 3/4 horsepower motor, we need to follow a few steps. Firstly, calculate the total load. The heater rating is 15 kilowatts. Convert the motor rating from horsepower to kilowatts. Given that 1 horsepower is equal to 746 watts, we can calculate the motor's power in watts by multiplying 3/4 horsepower by 746 watts per horsepower, which equals 559.5 watts. Now convert this to kilowatts by dividing by 1000, which gives us 0.56 kilowatts. Add the heater rating and the motor rating to find the total load. 15 kilowatts plus 0.56 kilowatts equals 15.56 kilowatts. Secondly, determine the current draw. We'll assume a voltage of 240 volts, which is typical for residential subpanels. To calculate the current draw, divide the total load by the voltage. 15.56 kilowatts converted to watts is 15,560 watts. Dividing 15,560 watts by 240 volts gives us a current draw of 64.83 amps. Thirdly, select the subfeed cable size. Based on the calculated current draw, we need to choose a cable with an ampacity that meets or exceeds 64.83 amps. An 8 American wire gauge copper cable has an ampacity of 70 amps, which exceeds the calculated current draw. Therefore, an 8 American wire gauge copper cable is the minimum required size. Keep in mind some additional notes. A subfeed cable should be properly sized to meet the National Electrical Code requirement. The subfeed cable should be protected by an appropriately sized circuit breaker or fuse. The subpanel should be properly sized to accommodate the total load and the number of circuits being fed. Always consult the NEC for specific requirements in your area. When dealing with electrical installations, it is crucial to adhere to safety standards and local codes. Ensuring proper grounding and bonding is essential for safety and preventing electrical hazards. Before working on any electrical system, always de-energize the circuit and verify it is de-energized using appropriate testing equipment. Remember that electrical work can be dangerous, and it's always best to consult a qualified electrician if you are not comfortable performing the work yourself. Considering the voltage drop is also important, especially over longer distances. Voltage drop occurs when the voltage at the load end of a circuit is less than the voltage at the source end. Excessive voltage drop can cause appliances and equipment to operate inefficiently or even fail prematurely. To minimize voltage drop, select a larger cable size than the minimum required by the ampacity calculation. The NEC provides guidelines for voltage drop in branch circuits and feeders. Generally, a voltage drop of no more than 3% in branch circuits and 5% in feeders is recommended. Consult NEC Chapter 9 Table 8 for conductor properties, including resistance, which is needed to calculate voltage drop. Use the formula voltage drop equals 2 times the length in feet times the current in amps times the resistance per foot, divided by 1000. Consider using aluminum conductors instead of copper conductors. Aluminum conductors are less expensive than copper conductors, but they have a higher resistance. This means that a larger size aluminum conductor is required to carry the same amount of current as a copper conductor. Aluminum conductors are often used for service entrance cables and feeders, where the larger size is not a significant issue. When using aluminum conductors, be sure to use connectors and terminals that are rated for use with aluminum. Aluminum and copper are dissimilar metals, and corrosion can occur if they are directly connected. Using the proper connectors and terminals will prevent corrosion and ensure a reliable connection. It's also important to consider the ambient temperature when selecting a conductor size. The ampacity of a conductor decreases as the ambient temperature increases. This is because the conductor generates more heat at higher temperatures, and the insulation may not be able to withstand the higher temperatures. The NEC provides ampacity correction factors for different ambient temperatures. These correction factors should be applied when selecting a conductor size. The type of insulation used in the conductor also affects its ampacity. Some types of insulation are rated for higher temperatures than others. The NEC provides ampacity ratings for different types of insulation. Be sure to select a conductor with an insulation rating that is appropriate for the application. In addition to the ampacity of the conductor, it's also important to consider the interrupting rating of the circuit breaker or fuse protecting the circuit. The interrupting rating is the maximum amount of current that the circuit breaker or fuse can safely interrupt. If the interrupting rating is too low, the circuit breaker or fuse may fail to interrupt a fault current, which could result in a fire or other hazard. The interrupting rating of the circuit breaker or fuse should be equal to or greater than the available fault current at the point where the circuit breaker or fuse is installed. The available fault current can be calculated using a fault current calculator or by consulting with a qualified electrician. When installing a subpanel, be sure to follow all applicable codes and regulations. The subpanel should be installed in a location that is readily accessible and protected from physical damage. The subpanel should be properly grounded and bonded. All wiring should be properly installed and terminated. It's also important to label all circuits in the subpanel so that they can be easily identified. This will make it easier to troubleshoot problems in the future. Before energizing the subpanel, be sure to inspect all wiring and connections to ensure that they are properly installed. Use a multimeter to verify that the voltage is correct and that there are no shorts or ground faults. If you are not comfortable performing these tasks, consult with a qualified electrician. They have the knowledge and experience to safely install and maintain electrical systems. Now let's delve a bit deeper into the NEC requirements related to cable sizing. The NEC provides tables that list the allowable ampacities of conductors based on their size, insulation type, and temperature rating. These tables are found in NEC Article 310. Remember to use the correct table for the type of conductor you are using and the conditions under which it will be installed. The NEC also provides adjustment and correction factors that must be applied to the ampacity values in the tables. These factors account for things like ambient temperature, the number of conductors in a raceway, and the presence of harmonics. Always apply these factors correctly to ensure that the conductor is properly sized. In some cases, it may be necessary to upsize the conductor to account for voltage drop or other factors. For example, if the voltage drop is excessive, you may need to use a larger conductor to reduce the resistance and minimize the voltage drop. The NEC provides guidelines for calculating voltage drop and determining the appropriate conductor size. It's also important to consider the type of load that the subpanel will be serving. Some loads, such as motors and heating elements, have high inrush currents when they are first turned on. This inrush current can be several times the normal operating current. The NEC requires that conductors be sized to handle these inrush currents. For motors, the NEC provides specific rules for sizing conductors based on the motor's horsepower rating and other factors. These rules are found in NEC Article 430. For heating elements, the NEC requires that the conductors be sized at 125% of the nameplate current rating of the heater. This is to account for the fact that heating elements can draw more current than their rated value. When sizing conductors for a subpanel, it's also important to consider the future needs of the subpanel. If you anticipate adding more loads to the subpanel in the future, you should size the conductors accordingly. It's always better to oversize the conductors slightly than to undersize them. It is very important to review NEC Table 310.15b16 for allowable ampacities of insulated conductors rated up to and including 2000 volts with not more than 3 current-carrying conductors in a raceway, cable, or direct buried, based on ambient temperature of 30 degrees Celsius. Or review NEC Table 310.15b17 for single insulated conductors rated 150 volts to 2000 volts in free air, based on ambient air temperature of 30 degrees Celsius. Make sure to follow the notes at the bottom of these tables for any adjustments or corrections to the ampacity. Additionally, ensure the equipment is properly labeled and meets the listing requirements of a recognized testing laboratory such as Underwriters Laboratories, or all. Be sure that the devices are installed per manufacturer's instructions. Consider the short circuit current rating of the panel board. Panel boards shall have a short circuit current rating not less than the available fault current. Now let's think about the 3/4 horsepower motor. 3/4 horsepower is equal to 0.75 horsepower. To convert horsepower to amps, we need to know the voltage of the motor. Since we are using a 240 volt system, and we are presuming this to be a single-phase motor, we use NEC table 430.248. From the table, a 3/4 horsepower motor at 240 volt single phase has a full load current of 4.8 amps. Now we can use this information to determine the wire size for the motor. Use NEC 430.22 to determine the conductor ampacity. Conductors supplying a single motor shall have an ampacity of not less than 125% of the motor's full load current. So 4.8 amps multiplied by 1.25 gives us 6 amps. The wire must have an ampacity of at least 6 amps. Reviewing NEC table 310.15b16, we see that a 14 American wire gauge copper wire is rated for 15 amps, which is greater than the 6 amps required. So, a 14 American wire gauge copper wire would be sufficient for the motor. Also, the overcurrent protection for the motor branch circuit must be considered. Review NEC 430.52. Based on NEC table 430.52, the maximum circuit breaker size for a single-phase motor is 250% of the motor's full load current if using an inverse time circuit breaker. 8 amps multiplied by 2.5 equals 12 amps. Since circuit breakers are typically available in standard sizes, a 15 amp circuit breaker would be used. Therefore, the 3/4 horsepower motor requires a 14 American wire gauge wire protected by a 15 amp circuit breaker. Ensure that all connections are made properly and torqued to the manufacturer's specifications. Using a torque screwdriver is important to prevent loose connections which can cause arcing and overheating. Always use appropriate personal protective equipment such as safety glasses and gloves when working with electrical equipment. Verify that the equipment is energized using a voltage tester before working on it. Consult with a qualified electrician if you have any questions or concerns about the electrical installation. Following these guidelines will help ensure a safe and reliable electrical system. Also consider derating factors based on the number of conductors in a conduit. If there are more than 3 current-carrying conductors in a conduit, the ampacity of the conductors must be derated. The derating factors are listed in NEC table 310.15 cone. For example, if there are 4 to 6 current-carrying conductors in a conduit, the ampacity of the conductors must be derated to 80% of their original value. If there are 7 to 9 current-carrying conductors in a conduit, the ampacity of the conductors must be derated to 70% of their original value. The neutral conductor is considered a current-carrying conductor if it carries more than a negligible amount of current. This can occur in circuits that serve nonlinear loads such as computers and electronic equipment. Harmonic currents can flow in the neutral conductor, which can cause it to overheat if it is not properly sized. In these cases, it may be necessary to upsize the neutral conductor to handle the harmonic current. The NEC provides guidelines for sizing neutral conductors in circuits with harmonic currents. Ensure to properly bond the subpanel enclosure to the grounding electrode system. This ensures that the subpanel is properly grounded and provides a path for fault current to flow back to the source. The grounding electrode system typically consists of a ground rod, a water pipe, or a concrete-encased electrode. The grounding electrode conductor connects the subpanel enclosure to the grounding electrode system. The size of the grounding electrode conductor is determined by NEC table 250.66. Remember, electrical work requires precision and attention to detail. Double-check all connections and measurements before energizing the circuit. If you are unsure about any aspect of the installation, consult with a qualified electrician. They can provide guidance and ensure that the installation is done safely and correctly. When running the cable, be sure to protect it from physical damage. Use conduit or other protective measures where the cable is exposed to potential damage. Avoid running the cable in areas where it could be easily damaged by vehicles or other equipment. When terminating the cable, be sure to use the correct connectors and terminals. Use connectors and terminals that are rated for the size and type of conductor being used. Tighten the connectors and terminals to the manufacturer-specified torque. Over-tightening can damage the conductors or connectors, while under-tightening can result in loose connections. Label the wires appropriately at both ends of the cable. This will make it easier to identify the wires in the future if you need to troubleshoot or modify the circuit. Use a permanent marker or label maker to create clear and easy-to-read labels. Wrap the labels around the wires so that they are visible from all angles. Before energizing the subpanel, inspect all wiring and connections to ensure that they are properly installed. Look for any loose connections, damaged conductors, or other potential problems. Use a voltage tester to verify that the voltage is correct and that there are no shorts or ground faults. If you find any problems, correct them before energizing the subpanel. Take your time and do the job right. Electrical safety is paramount. Following these steps will help ensure a safe and reliable electrical system. Before starting any electrical work, be sure to obtain all necessary permits and approvals. Contact your local building department to determine the requirements in your area. The building department may require you to submit plans for the electrical installation and may require an inspection after the work is completed. Complying with all applicable codes and regulations is essential for ensuring the safety and legality of the electrical installation. And finally, after completing the electrical installation, document all work that was performed. Keep records of the materials used, the measurements taken, and any problems that were encountered. This documentation will be helpful in the future if you need to troubleshoot or modify the circuit. It will also be helpful if you ever decide to sell your property. Electrical permits and inspections are a vital part of the process for ensuring safety and compliance with regulations.